The deepening reason your chest tightens on a cliff edge isn't fear, it's instinct. Your nervous system knows something your eyes can't see. And in 2023, 70 miles off the California coast, a canyon the size of the Grand Canyon collapsed its own walls inward, swallowing cables, research equipment, and 17 years of seafloor data in a single catastrophic surge. Scientists were watching. They couldn't stop it. This isn't a story about somewhere distant. The Monterey Canyon sits at the edge of one of the most densely populated coastlines on Earth. The canyon head, the mouth, the opening, begins less than 100 meters from shore. Not miles, not kilometers, 100 meters. If you've ever stood on a California beach and looked west, you are standing at the edge of a geological force that has been in active collapse for at least 10,000 years. And here is the part that changes everything. It's not slowing down. If anything, storm after storm, tide after tide, it is accelerating. Scientists know it. They're watching it happen, and they cannot stop it. The Monterey Canyon is deeper than the Grand Canyon at its lowest point, over 3,600 meters down, deep enough to swallow a small mountain whole. But the thing that makes it terrifying isn't the depth. It's the turbidity currents. Picture an avalanche, not snow, water. Dense, sediment-choked water moving at 40 miles per hour, scraping the canyon floor, shearing off walls, carrying boulders the size of houses as if they weigh nothing. These currents don't announce themselves. They trigger in seconds from a single wave, a storm drain flush, even a small earthquake tremor. In November 2016, a turbidity current ripped down the canyon and snapped multiple deep-sea sensor cables simultaneously. Researchers at the Monterey Bay Aquarium Research Institute had designed those instruments to withstand anything the ocean could throw at them. The canyon threw something else, something that couldn't be predicted from the surface, something still happening right now beneath the water while you breathe. Here is what you were not supposed to know. The canyon doesn't need an earthquake to collapse. The single biggest trigger for its ongoing failure isn't tectonic, it's you. Storm water, urban runoff. The pipes that drain your city's streets empty into Moss Landing Harbor directly into the canyon head. Sand and sediment pile up at the rim. Then it goes over, not slowly, not predictably. 1 hour the ledge is stable. The next it's gone. Scientists tried sediment barriers. They tried monitoring nets. They tried predictive modeling. A model built to forecast the next major turbidity current predicted a 6-month window of stability. The current happened 11 days later. The model was right about one thing. The canyon doesn't care what the model says. This is where it gets personal. The Monterey Canyon isn't just eroding, it's migrating. Headward erosion, the process by which a canyon's mouth moves inland over time, is actively pulling the canyon closer to the shore. This isn't theory. Scientists have documented its creep. At current rates, the canyon head advances roughly 1 meter every year. That sounds small. It isn't. That's a meter of bedrock, a meter of California coastline permanently gone. In 10,000 years, it advanced to where it stands today. In the next 10,000, it moves again. But here is what the geological record also shows. It doesn't always move gradually. There are signatures in the sediment layers, violent markers, sudden jumps, catastrophic retreats where the canyon advanced not a meter but hundreds of meters in a matter of months, triggered by events. Earthquakes, storm clusters, rapid human alteration of sediment load. The last great jump happened roughly 11,000 years ago at the end of the last ice age, when sea levels rose rapidly and coastal sediment dynamics shifted overnight. Geologically overnight. What researchers will not say on camera, what they'll tell you only in print, buried in papers written in passive voice, is that the conditions for another catastrophic jump exist right now. The slope angles, the sediment accumulation, the seismic background noise, every variable is present. The only thing missing is the trigger. The internet runs through that canyon, literally. Trans-Pacific fiber optic cables, the physical lines carrying your data, your calls, your financial transactions across the ocean, are laid along the canyon floor and walls. When the 2016 turbidity current hit, it didn't just destroy sensors, it severed lines. The internet didn't go dark. Redundancy exists for exactly that, but traffic rerouted, latency spiked. and for 24 hours the most connected coastline in the world ran on backup. If a larger event triggered, the outcome wouldn't be 24 hours. Engineers have proposed burying the cables deeper, armoring the walls, rerouting the lines. Each proposal has been modeled. Each has a fatal flaw. The canyon is too active, too unpredictable, too powerful. You can harden the cables. You cannot harden the canyon. Scientists monitoring the canyon in real time documented something they haven't yet fully explained. A series of small, rhythmic pressure pulses along the eastern wall. Not an earthquake, not a storm, not a turbidity current, something else. Something that repeats on a cycle, something that gets measurably stronger each pass. They've named the pattern. They've mapped it across 18 months of data. What they haven't done, what no one can do yet, is tell you what it's building toward, or whether it's ever going to stop.